In Lecture 6, we continue our discussion on 1D transient conduction, now with radial geometries. It's going to be very similar. The analysis is the same as with a flat plate or an X spatial variation. Only we'll have a different solution available to us for theta star. Okay, radial systems. I'm just going to talk through the notes and then we'll work one example. For radial systems, we're going to consider two cases: an infinitely long cylinder. Long means that the length is 10 times longer than the radius, and so this allows it to effectively be a one-dimensional spatial problem, so that the temperature will only vary in the r direction. If it were a short cylinder, you might argue that there's also a variation in the x, or excuse me, this would be the z direction. Long enough cylinder, then we still have a 1D transient situation. And for a sphere, of course, there's just r anyway. There's an r direction as a function of time, and also as a function of time. So we're looking for t now as a function of r and time rather than x and time. And we'll have two different solutions to consider these separately, but the scales for the problem are the same whether you're dealing with an infinite cylinder or a sphere. It's just a different solution. The governing equation is actually different between these and also in comparison to a flat plate. We don't need to go into the details of the differences in the governing differential equation because we actually have a solution that's already been made available to us. It's a scaled solution, so we need to know what the scales are so that we can appropriately convert their dimensionless solution into our particular physical dimensional problem. Okay, so the position is now r. If we scale r by the maximum value r could be is the outer radius, r outer, so r naught is the outer radius. R over R naught is our new dimensionless position, R star. So R star is going to vary between 0 and 1 on the outer side. The time scale is actually the same time scale. Before, if you remember, we had L squared over alpha for a time scale. Now the length instead of L is R naught. So it's R naught squared over alpha is the time scale. So this is our definition for T star and for the Fourier number. Remember before when I said the time scale, and as I did now, is R naught over alpha, the time scale would be in the denominator of this equation. So that is R squared over alpha. Alpha over R naught squared is actually a 1 over time unit. Theta is the same. T minus T ambient over Ti minus T ambient. And now the BO number that shows up in the solution, remember our solution is dependent on the BO number. The BO number that shows up in the convection boundary condition, the length scale is R. So it's H R naught over K. Okay, so we're not using R naught over 2 or R naught over 3 as we did for the BO number check. Still use this BO number to check whether or not you can assume lump capacitance. When you find out from this BO number that you can't, and now you need to use this solution, for example, for an infinite cylinder, this is the BO number that you need to use when you're calculating eigenvalues here. Infinite cylinder solution is given to us as a summation again, so still in terms of a Cn and a zeta n. That's the eigenvalue, and these are the magnitude of each of the terms. Instead of a cosine here as we had for the x problem, we have a Bessel function of the first kind. And still have this same exponential term. Remember, Fourier number is the same thing as T star. New definition of the Fourier number now, right? We have R squared over alpha for the time scale. These C's are actually different. That's a different formula. And this is a different transcendental equation for zeta n. This defines the eigenvalues. So technically, you could try to solve for the roots of this equation for a given BO number yourself. Take those roots and substitute them into this formula to calculate your Cn's. You can do the work to solve for all your C values and zeta values and compute as many of these terms as you want to. However, Hopefully you can get away with a one-term approximation if your Fourier number is large enough, in which case you're only going to need a C1 and a zeta 1, and this summation turns into a single term. Okay, so for the Bessel functions, you'll need those for the cylinder for considering these infinitely long cylinder problems. So that is in Appendix B4. I think you're familiar with those. Table B4, here's the Bessel functions of the first kind. So you have values for J1 and J0 in terms of X, and you simply need to interpolate to use these. You also have some Bessel functions of the other kinds given to you, but that's all you need for these. Okay, so we use the same scales, and we can consider the solution for a sphere. So it has a sine function here in comparison, and there's a 1 over r term here. So r naught shows up twice, so that's different regarding the sphere solution. Still have this same exponential decay. Right, that is t star. And so there's, again, different definitions of the Cn and zeta n values that correspond to the Biot number. Hopefully we're going to use the one-term approximation. Biot number is greater than 0.2. We can assume one term is accurate enough, and so you just need a zeta 1 and a C1, and these values are already tabulated as a function of the Biot number in table 5.1. So you don't need to actually even deal with these expressions and solve those directly. You only need, for a one-term approximation, need to use table 5.1. So here is table 5.1. Right, we have zeta 1 and C1 values for three different cases: the plane wall, infinite cylinder, and a sphere, as a function of the Biot number. So this Biot number is not the critical Biot number. This is the Biot number with the full length scale, right? Either an L or an R naught. And so you need to interpolate to get the appropriate values of zeta 1 and C1 as the Biot number approaches infinity. So, and that allows you to model an isothermal wall. Those are provided at the very bottom of this table. Also be careful, for some reason it's popular to mix up these two in your analysis. They are often kind of close in size, and I guess this maybe looks a little bit like that C1, but make sure you pay attention to get the right numbers that correspond to a zeta 1 and a C1, and for the appropriate situation. We're going to work an infinite cylinder example. Okay, so for isothermal boundaries, just like for the flat plate case, let Biot number go to infinity. Replace T ambient with Ts. That's the temperature that you are instantaneously imposing at this surface to be an isothermal boundary. Use the case where Biot number goes to infinity, and that'll provide you the spatial variation for an isothermal boundary condition inside, just like for the flat plate problem we worked earlier. I think it was a sheet of glass. Alright, so let's work an example. So we have a very long nichrome cylinder, 10 centimeters in diameter. It's initially at 300 degrees C, so very long just means more than 10 times. It's long enough such that we only need to worry about the temperature variation in the R direction spatially. It is suddenly quenched in an oil bath that maintains 40 degrees C and an H of 280. Determine the temperatures at the center and again on the surface 5 minutes after we begin this quenching process. Alright, so I'm going to draw our cylinder. Convection, H is equal to 280 watts per meter squared K. T ambient was 40 degrees C. This thing starts off initially at a uniform 300 degrees C, so it starts out pretty hot, and then we're going to start to quench this. The diameter is, so D is equal to 10 centimeters. R naught then is equal to 5 centimeters, right? So 0.05 meters is the radius. We need to find T at R equal to 0 and T at R equal to R naught at T equal to 5 minutes. If lumped capacitance were valid, then these two would arguably be the same after 5 minutes, or really, really close to one another. Okay, so the first thing to think about is we are going to need properties to evaluate the BO number. So remember, properties are kind of critical in these problems because the properties vary with temperature, and the temperature is varying throughout the problem. Typically, we're just going to use the density at 300 K. So the density of this nichrome is 8,400 kilograms per cubic meter. For the K values, I'm going to go ahead and write down what I found in the table at the various temperatures at 400 K and at 600 K and again at 800 K. From the tables, they give us a K and a C sub P. K is for 400 14, for 1600 is 16, and for 800 is 21. The units are our standard units, watts per meter per K per Kelvin. At 400 degrees, C sub P is 480. Sorry, that's not the units for C sub P. 480. 525 at 600 and 545. The units of this are a kilojoule. Sorry, a joule. Not a kilojoule. A joule per kilogram K. Okay, so we need to figure out what would be the appropriate temperature to estimate these properties at, right? So we're going to use T average. We need to estimate at T average. Unfortunately, after 5 minutes, we don't know what the temperature is going to be. That's what it's asking for. We do know that it's going to be somewhere between 300, right? The temperature is going to start to drop. It's going to be somewhere between 300, and it will never get lower than 400. So just to have some type of inclusion, we're just going to have to make an average between these two. We don't have another number. We could iterate and do an average, evaluate what those temperatures are, and then repeat an average and do it maybe one more time. But I think it's okay to just use the average of 400 degrees C and the 300 degrees C. So this comes up to be 170 degrees C or 443 K. Alright, so we need to interpolate at 443 K somewhere here. What I get for that is 14.43 watts per meter K for the thermal conductivity for C sub P, 489.7 joules per kilogram K. The variation in these is quite often significant enough to kind of drastically change the temperatures at the end after 5 minutes, or change the time, whatever it is it's asking for. Okay, so now we need to check for lump capacitance. We don't expect it in this case, since I'm working an example with a spatial variation, but still check for lump capacitance. If we can get away with that, then we would still use a lump capacitance analysis. So BI check is going to be equal to H times, for a cylinder, R naught over 2 divided by this K. This comes out to be 0.485, greater than 0.1. Right, so the answer is no. No lumped capacitance. So we're going to have to include a spatial variation in our analysis. The next question actually is going to be, can we do a one-term approximation when we include our spatial analysis? So we know that the duration of this experiment is 5 minutes, so we can go ahead and calculate a Fourier number, right? T star is equal to the Fourier number. That's T divided by R naught squared over alpha. That's our time scale in this problem. Right, so we can now use 5 minutes, evaluate this at 5 minutes, T star at, let's put 5 minutes, VO number at 5 minutes, comes out to equal 0.421. Right, that's greater than 0.2. Right, so that implies a one-term approximation is valid. Okay, so the one-term approximation, we don't need to worry about the summation. We can look up for a cylinder. Theta star is equal to C1 J naught zeta 1 R star times e to the minus zeta 1 squared T star. Zeta 1 and C1 are going to depend on the BO number. The BO number they depend on is H R naught over K. This comes out to be 0.97. Okay, now with 0.97 as a value of a BO number, we'll go to table 5.1. Alright, go down to 0.97 here. Right, in between these two, interpolate over here on these two columns correspond to the infinite cylinder. So zeta 1 is going to be somewhere between 1.2 and 1.25. Right, C1 is going to be somewhere between 1.1 and 1.2. Okay, so after I perform the interpolation, I get C1 is equal to 1.20203. Zeta 1 is equal to 1.2408. Okay, so good example to show how these numbers can actually end up being very, very close. So be careful to keep those separate appropriately. Okay, remember that theta star that shows up there is T minus T ambient divided by Ti minus T ambient. Okay, so now finally the question is we need to find T at, let's go ahead and put parentheses here, T at 0 for R, time is 5 minutes, and then again T at R naught for R, the time is 5 minutes, right? So this is the surface temperature, this is the midplane temperature. We might call that Tm and call that T surface. Alright, so let's do the R equal to 0 case. At R equal to 0, theta star, we're given a temperature for theta star, or an equation for theta star, is equal to C1 J naught zeta 1. 0 goes in place of R star. Times e to the minus zeta 1 squared Fourier number, or T star. It turns out that J naught at 0 is actually equal to 1. J naught at 0 is equal to 1. Okay, so this is 1. And theta star, so theta star is now equal to C1 e to the minus zeta 1 squared times a Fourier number. Right, this Fourier number is 0.421. Right, that zeta 1 that shows up here is, what's our value for zeta 1? 1.2408. Right, and that C1 is 1.20203. So we can substitute and solve this. This will be a dimensionless answer, and the n theta star comes out to equal 0.6287. Ultimately, what we want is the temperature, right? That's T minus T ambient over Ti minus T ambient. So solve this for T. T is equal to Ti minus T ambient times theta star plus T ambient. So if I take this number for theta star, so this is actually theta star at R star equal to 0 and T star equal to 0.421 for that value, right? That goes here. So temperature at R equal to 0 and 5 minutes is now equal to Ti minus T ambient times 0.6287 in place of this theta star plus T ambient. Oh yeah, plus T ambient. This comes out to be 203.5 degrees C. Okay, so now we need surface temperature. At R equal to R outer on the outside, that implies R star is equal to 1, right? Because R star is equal to R over R naught. So now we're going to again evaluate theta star. Now it's C1 J naught zeta 1 R star. Now the R star goes to 1 e to the minus zeta 1 squared Fourier number. So now we must evaluate J naught of zeta 1. Zeta 1 is, what is zeta 1? 1.2408. So come in here, go to 1.2408 and interpolate a J naught from this. I get 0.6503. So substitute in the rest of these numbers. Theta star at R star equal to 1. T star is equal to 0.421. This is equal to 0.40884. So finally, the temperature at R equal to R outer, T equal to 5 minutes, is going to be equal to Ti minus T ambient times that 0.40884 plus T ambient. This answer is 146.3 degrees C. So it is significantly cooler on the outside surface than it is internally. It's 200 degrees C. So there is definitely a spatial variation, a spatial dependence over R for this problem during this quenching process. Okay, so I think the process is pretty straightforward that you could repeat this for a spherical case. There is some example problems involving a sphere on the sample exam problems that I've given you. I'm going to leave that for you guys to work, especially since it's a take-home exam. You'll have plenty of time to work through any new details that are necessary for that. Good luck with your studies in preparation for the exam.